So, but speaking of Wooga, I guess not everybody knows us yet. So Wooga does social games, as we heard, mostly published on the Facebook platform. One of our games, it's called Monster World, looks like. As you can see, it's all cute and colorful, which might be the reason why a lot of women actually are playing the Wooga games as well. Actually, the majority of players are women, like 70% or something. Yeah, but that's not what I want to talk about today. So I want to talk more about what powers these games. So here's a typical architecture overview. So the game itself is usually implemented as a separate application. When it's published on Facebook, it will usually be a Flash application, but it might also be a native iOS app or anything else, really. And it talks through HTTP API to some backend running in a data center. So the backend part is what I want to focus on today. And actually that's just a bit of a glorified web service, if you will. So it provides something like 100 API functions for a typical game. And the client will usually use these API calls in an asynchronous way because we don't want our players to wait for a response. So we care more about the overall throughput of the system than the actual latency, which is also nice to be low, of course. So what are the responsibilities of this backend? Basically, it will keep the game state, and through the API calls it will change the state, it will update the state. It will also, of course, validate if a certain transformation is valid at the given time. So we don't want to play everybody by its own rules, but actually by the game's rules. So we need to make sure that this all makes sense. The backend will also, of course, persist the game state. The scale is actually pretty interesting. Yeah, that's just a high number for this Monster World game. We're getting about 14 billion of these API requests per month. I don't know if everybody has a feeling if that's totally much or not, but there's one website that kindly publishes its backend calls, and that's called Wikipedia. Maybe some of you have heard of it. So that's in the same ballpark. They also have like 14 to 15 billion page views a month. Well, that's the only way I'm going to compare us to Wikipedia, because I mean, they do this great stuff for humanity, and we just suffocate. But in fact, Wikipedia has it a bit easier than us in because what they can do, they can cache. The pages do change, but they, compared to the views, it's a percentage, I guess. And for us, this boils down to about 100,000 database operations per second, of which half are actually updates. So caching is not really something that would help. Yeah, so that's what we're up against, and how do we deal with it? I think this is pretty unique. At least I haven't encountered this in any other company, because usually you have pretty small teams, and these are independent, as in really independent. So what we got to do last summer, namely thinking about how we want to do our system, is what every team gets to. So we can choose your weapons freely. But whatever you choose, you're also responsible for the operations of the system you build afterwards. And as the people building the backend are usually also just a small part of this already small team, so maybe 2 or 3 backend developers per game, you better choose wisely what you can run and support afterwards. So this, yeah, everybody does what he likes kind of thingy. Could lead to total chaos, but combine this with a culture of sharing and the need to take responsibility afterwards for what you produce, really works. Yeah. So it's a really a very open culture, so there are no repos you wouldn't have access to, so you can always look what other teams did, and you can also pick and reuse stuff, but you won't be forced to in any way, so there are no like company libraries, frameworks, whatnot. And yeah, so instead of having total chaos, this has actually produced this landscape of games that are live currently. So you see the games logos on top, and then the dominant programming language for the backend, and below that the storage solutions, or the main storage solutions that games use. So as you can see, we had a lot of success with Ruby, but also Erlang gets a lot of adoption lately. You see, as you can see to the right, you can also read this a bit as a timeline, so from left to right. So the most recent one is actually the Erlang one. And there's just 3 more erlang-based backends in the pipeline. So it's really taking off into the big time. There are 2 very different basic architectures in this landscape. So throughout various backends. So one is this stateless, so-called stateless application server approach, which is very common when you do web applications. So if you have a server that answers your requests and it has some storage or database in between, when the request comes in, it will then kind of read everything it needs to process the request from the database, also update some stuff, and then finally generate an answer. And then it does it for the next request again. So as if nothing happened before, it will happily load everything it needs to process the request again and again and again. And as you can see, this puts a lot of load on the database, which is also kind of visible in the numbers. I said earlier, this is 50,000 updates. So the database can quickly become a bottleneck. So, and yeah, when the database becomes a bottleneck, then of course you do sharding, right? You just have to have the load balancer on top, a couple of app servers behind that, and then the shared database. When one is not enough, you just use a second one. When that's not enough, use a couple of more. Should you have trouble with sharding, then you're just not using enough of it. And as a colleague of mine recently put it, these stateless application servers basically guarantee one thing, and that is the data is never very needed. But there is hope. I mean, if you really look into the pattern that is interaction with the user, what it looks like, then you will see that it has a strong session pattern. So if you imagine the user starts playing at a given time, then we will play for a while. Usually we will do many transformations of the same set of the data, namely the game state, about 100 interactions usually per session when the user plays, and then he will just stop and maybe hopefully come back later, like next day or in 8 hours or something. So this is something you could also approach like this. So imagine you have this server with an incoming request, and we just load the whole game state when it kind of spawns up. And then it just keeps running, and it just keeps the whole game state in memory, and it will happily answer all the interactions, all the requests that the user generates, which then initializes this one game session of the user, and once he's done with that, then you just dump it all back to this. You can also dump it periodically in between, but you get the point. So there's definitely a lot less stress on players. So this one process per active user, being a stateful game server, would then hold the entire game state, the current game state, in memory, and it's the only one that can interact with this. So you have strong encapsulation. And as this is one process, and if you mentally map this to Erlang, then you will know that this one process will have a mailbox and it will process all incoming commands it receives one after the other. So you have a very nice concurrency control. You need not fear that two application servers would kind of access the same data, or even modify the same data at the same time, and you need to protect yourself against that with locks or anything. So you have a nice concurrency control through the actor model. And as I said, it loads the game state basically once and writes it back just periodically, or when timeout occurs, so the user hasn't interacted for a while, and it can just dump it back to this. Yeah, and that definitely solves the bottleneck problem with the database. So if you had a game with like 30-second database operations, with a stateless approach, the stateful approach would then yield like 700. Yeah, I guess we can handle that. And this is actually the architecture in place for the Erlang backend we have live. And I guess a couple of you might have seen the awesome presentation that Knut and Paolo, colleagues of mine, Knut is here as well, presented on the last Erlang user conference. So it is also available online, so if you want to know a bit more about this whole architecture and how this all works, especially in the Erlang world, dig into it. So that was kind of what I found when I came to Wooga. So the question was how to innovate that. You put yourself in my shoes, you know. Done. I think it's pretty obvious that the stateful approach is very superior to the stateless one. So that was clearly the way to go. We wanted to keep this. And also Erlang had already proven itself as a very reliable and very easy to operate system. So it also made sense to continue down this path. But yeah, you know, first world problems. Really all the way. When you've done some Ruby as I did before, it also felt a bit like giving up a lot. So we set out to maybe combine Erlang and Ruby. So while Erlang is obviously great for concurrency, it's robust and great for all things operational, Ruby is also great. And it is much more concise and expressive in its syntax, I think, and it's also super flexible, so you can easily kind of mold it in whatever DSL-like thing you want to express your program, and that's something that's really great for development. Oh yeah, this guy also kept haunting us a bit, so I must say certainly Akka and JRuby would also be something to take a very close look and use the JVM for the backend. And I'm sure a future team at Wooga will do exactly that. But at the time being, I wasn't entirely sure that I want to put up with this. So it would have been an entirely new stack, both development-wise, although there were some people at Wooga that had quite a bit of Java and JVM experience. But still, I mean, especially for our team, it would have been pretty new, and also for operations, so there was no real operational experience running an Akka-based system. So that's why we more or less unscientifically ignored this option and just tried out this hybrid approach of Erlang and Ruby, and kind of just went forward with it and said, yeah, we will do this until we hit a roadblock or something. Let's just start out with it. So yeah, bringing the two worlds together. As I said, the Erlang part would be the one that has these processes, one per game session, holding the state. So how do you hook this up now to Ruby? We were imagining it to just send it out to some workers running the Ruby code. So these would then do the state transformation, the game state, and then send back the new game state. So yeah, and we wanted to couple this most flexibly, and we ended up with 0MQ in between. So 0MQ is basically, I think their claim is sockets on steroids. So what they actually have, they have queue-like properties on top of TCP or Unix domain sockets, and are also in-process topologies supported. So it's really awesome queuing, progress, and lightweight and easy to use and whatnot. Super pro. I don't know, does anybody of you have heard of or even know a product called Mongrel 2? Okay. Yeah, quite some. So, the Mongrel 2, it's a web application server that has a similar idea, and it would also be kind of language agnostic in hooking up its applications through 0MQ. So as this was already thought through quite well, we just adapted the exact same queuing layout and also the message format that Mongrel 2 uses. Which was just kind of a no-brainer to reuse this. Oh yeah, thanks for your insight, Clarence. Indeed, it is, in a way, it is stateless upside down, as the Ruby workers are still stateless, right? But instead of having a shared database behind them, they would get everything they need to know right with the request. So you can't have taken sharding to the max, as now every single user kind of has its own shard, namely this settle in Erlang. So that kind of eliminates the bottleneck, but it also introduces a new bottleneck. So the amount of data you have to pass into the worker for it to be able to do its transformation is something you have to keep an eye on, definitely. So that kind of thing, how much data goes back and forth. So just for your reference, more or less, how did we technically connect the two stacks? As I said, we use the Mongrel 2 protocol and 0MQ setup. Then we have some Erlang code that would help us generate messages compliant to this Mongrel 2 message format, and it also helps setting up the 0MQ sockets and stuff. That's also a GitHub. And then by adapting the Mongrel 2 setup, we could reuse quite a bit of stuff that was available in Ruby land. So there's a project called Mongrel 2 that will interface the Mongrel 2 messages to the REC protocol. In turn is the de facto standard of how you hook up applications to web server in Ruby land. So we could just use the common Ruby web framework, namely Sinatra in this case. So essentially, we were speaking HTTP over the zero queues and could have hooked up basically any Ruby-based web framework, also like Rails or whatever. Yeah, that's
a question. I'm trying to make it out in my head. So you have the state of each player in an Erlang process.
Yep.
Then you send the state plus an operation to a Ruby worker that does some blah 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 game logic, and then it sends back the new state to the Erlang process.
Yeah.
Okay. Thank you.
More or less, with one optimization. Yeah. So we set out to reason, and it was mostly the code. Yeah? So let's look at some code. Here's an example controller. As you can see, it specifies a game action. It kind of maps the game action to an URL pattern. And in this case, as you might be able to derive from naming, we're talking about a game where you can shake a fruit tree. And it goes on with kind of like, as I said, DSL is big strengths of Ruby. So this app.gameAction method we're calling here, it looks almost native to the language, but it isn't. So it's something we build, and it accepts a lot of parameters and options you can configure. And this also gives a pretty nice documentation. We actually do generate documentation from this. Yeah, and it's the code is basically just the parameter parsing and all up to some model. So it's skinny as controllers should be, as a Rails motto. And it can't get much less code. And the model in turn also benefits from Ruby in a way. So you can have things like inheritance. So our little fruit tree can happily inherit from a tree object or a tree class, and can, on top of the properties that the tree might already have, also define new properties. These are also in a declarative way. Again, it looks almost native to the language, but it's just us hooking up these properties to the kind of the message that will get sent back. So defining what the state of this tree looks like. And the action itself is also, everybody could understand what is going on here. Just increment the counter here, decrement the counter there, set some attributes, that's basically it. So this is like really easily testable in a way. And I think it's more or less a minimal amount of code you could write to do this. To address a bit the thing with how much data do you send back and forth, let me say the game state is split in multiple parts. So not every action needs all the game state. So it might be that one part is the user, or you also want to see the map, the world, kind of set out on this map like fruit trees. So while Erlang does not really care about the content of these parts, which are to Erlang just some binary, and in reality they are serialized Ruby objects, Erlang does need to know what action needs which parts. So it has to send in the right parts to enable Ruby to process the action. But that's also actually pretty easy. So if you look back to this controller code, there you have it, right? It's right there. So the action itself says which parts it needs to do its work. And so this Ruby worker knows the mapping for every action, and it can just push this information and start over to the Erlang core.
But the effects you need to know that the fruit tree shake operation actually affects the user.
Yeah.
Because you can't see that from this code.
That's true. That's true. That's indeed something we were struggling a bit on how to kind of do the encapsulation right there. There were also alternative approaches like passing the user around instead of implicitly referencing it through the session object. Yeah, we'll get a bit to that later. And what's also possible, of course, is just to provide another action that would allow Erlang to query this mapping at any given time. So imagine that you would have a restart in the Erlang server, and it would basically not know the mapping. It just has to query. That's all pretty sweet. And yeah, it was really nice to look. We had pretty beautiful code. Also deployment-wise, it's really a nice thing to just kind of deploy the new business logic without having to think about touching the session container, basically the storage. And it was also nice to scale, so you could just have more of the workers basically on one box, or 0MQ would also give you the option to have the workers on a separate machine if you would like to do that. But you could also just scale the whole thing, like Erlang plus Ruby with a couple of workers on multiple nodes, so it's just not a problem. Yeah, the performance was also good, I would say. Actually, there would be a penalty, of course. But as I said, it was easy enough to scale, so you could just kind of put more hardware, basically, and get it running. Unless you have another problem. Yeah. So, so while we were exploring these new backend concepts, also the game itself took shape more and more. And it kind of became apparent that this particular game that we were kind of tasked to support would rather gravitate to large chunks of game states that you would need for each action, and it would be rather hard to conceptualize against that. So we looked at the performance impact more closely, especially for larger payloads, like a payload that you would have to pass in and back. We compared what it would look like if you did a pure Erlang implementation for the game logic versus a Ruby one. And so we kind of measured the system, how much requests per second it could support. And we also did a couple of test series with different numbers of workers. So this whole thing was run on an 8-core machine, so we varied the amount of workers we had running between 1 and 8. And that's what it looked like for Erlang. So we could, even with this larger payload, we could easily support something like 4 or even more thousand requests per second. And the cost for doing the same thing in our kind of dream architecture in this scenario is indeed 1 order of a magnitude. So the approach, Erlang Ruby, we could only do 400 requests per second with the same box, which was an 8-core machine. But it's, I mean, 8-core sounds more powerful than this box virtual thing actually is, so it was in the Amazon cloud. But still, I mean, 1 order of magnitude, it's a bit tough to swallow that. So, and another thing, with a larger payload, it is no longer CPU bound. So, while with a smaller payload, we could easily saturate the box. It was not a problem. It looked really, really nice. But with a larger payload, we could only kind of utilize 25% of the box. So this looked, we didn't kind of dig too deep into it, but it looks like a kind of a fixed bandwidth limit. So it might be even a memory bandwidth limit. We hit there at about 300 megabytes per second, going back and forth between the two stacks. And that's not so nice to have such a end to scalability on a single box. So, and also we were kind of burned because something similar has happened before, also in this game months ago, I talked about earlier. The team back then hit a roadblock with the database technology at about 500,000 daily active users. And while they were already live and kind of successful and growing, it was really painful to then kind of rethink major parts of the architecture and kind of do this change and running the system. So, yeah, coming back to the happiness, I think the happiness lies indeed in the working product here. And even though it would have been super nice to do the whole system in this kind of developer-friendly, easily readable code and architecture we worked out, we still, in the light of these new facts, how the game progressed and how the actual product would look like, and the kind of the parameters it brought with it, we actually decided to go for an Erlang-only approach at this point in time. So this can be kind of considered almost a happy ending for this crowd, I guess. So, but still, yeah, not an easy decision to make. So again,
okay.
Yeah.
At this stage, did you consider using a port to a Ruby process instead?
Yeah, we tried ports as well. They perform a bit better than the zero-MQ approach. With a large payload about twice as good. But we would lose a lot of the other properties that we would like to have. Because when you have ports, then suddenly Erlang has to kind of control who it attaches to. And it would also need to distribute the workload onto the different ports.
Would we have the possibility to push the entire state down to the Ruby port then? I know that's different architecture. But you push the entire state to the Ruby port and just send the operations you want done with the current data you want to use.
So you're saying basically keep a kind of a replicate of the whole thing. Yeah, we thought about similar things with something like, say, Redis as an intermediate storage in between and stuff, but had properties that we didn't like so much because it would break the encapsulation, and still it was a trade. So, so the thing is that the best decision that we could come up with was really to explore this pure Erlang approach. We just did this, and here's some code how it would look. The same action basically would look like in Erlang. So this is what you see as more or less the controller side of things again. As you can see, it's still the same pattern. So you get some state in, and you get send the updated state back out. So yeah, fits nicely with a functional approach. In between that, there's a bit more legwork, I would say. So extracting the arguments, getting the right data structures to work on, and also building the whole thing. It's a bit more explicit. You have to just write more stuff to get the job done, but still. And as you see, this basically what we talked about earlier. In this case, here we have the controller also being a mediator, so it does not actually delegate the user modifications down to the shake model, shake action of the model. So here we are also dealing with the user modifications in the controller. While the model then is as trivial as it can be, so you just also have this shake thing and put the tree in and get a new tree back out and shake it up. Not so. That's super interesting, I guess. Yeah, and instead of having the properties on the simpler models, we could, for instance, also use the Erlang records, which map quite nicely to this problem. For more complex models, you would use other types like the dictionary or even just property lists or something, or nested property lists. But still, for simpler models, the reference of purpose. So, can there be happiness without Ruby? I'll say, in hindsight, yes, there can be happiness without Ruby. So, at this point, there might be kind of a bit less developer comfort zone, but on the other hand, we were now confident that we will be able to deliver a product that is really reliable and it will perform great and just great product. So, and that's where we draw our happiness from. Thank you. While you think about some smart questions, let me briefly mention that Wooga also is always looking for new developers. So if you want to follow down this path, you have the URL right there, and also you can hook us up. So I have two colleagues with me here, so Chris and Knut are with me, and I'm also willing to answer any questions regarding this talk or any other stuff later on. So, what are there any questions? Yes?
How do you dispatch the incoming API calls to the corresponding Erlang processes?
Yeah, so in this stateful approach, that's obviously something that is very needed because you really need to identify the node that runs the user's session. So we will have some sort of infrastructure, kind of a global registry that knows about what user lives on what server, and it would then just route the request to that. We will probably optimize it in a way that following requests can be routed directly, and it would just kind of need to be rerouted should the client do something wrong.
Are you using Amnesia for that?
Probably not. In the Magic Land game server, it's a single Redis instance basically, and we are looking into ways to swap that out from a distributed approach. But probably, either just some custom Erlang code, or even something like Zookeeper or whatever.
When you're sending the state between the distributor and the Erlang process reducer, is it all done over just Erlang distribution normal message passing?
Between which parts of the systems are you talking about?
Well, when it gets the state and puts it into the user worker.
In the hybrid approach?
No, in the
In the pure Erlang, yeah, this will just be in the same node, basically. So you have the session.
But does it pull in the session state from the database before it creates a worker, or in the worker?
There are no workers in this sense. It's just basically just code operating on the data structures. And when you spawn up in the user session and we start playing, then we will initially load the whole game state.
You mentioned the user state is stored in the Erlang process.
Yeah.
And do you consider replicating this state away, for example, to Amnesia for high availability?
No, not really. While we could do this, we were also thinking about maybe using something like Ria Core and to have like multiple replicas and stuff. But in reality, I mean, the worst thing that could happen if we kind of persist this stuff too infrequently and the server process would crash, all that would happen is that the user would then lose a bit of progress in the game. So, and as we don't do banking or anything, this is totally acceptable and just an easier systems approach. So that's where we go with that. Yeah.
So what algorithm do you use for pushing the information back into the data store? So presumably the user walks away, they get bored or whatever it is, at some point you're going to tear the connection down. So what do you do?
So basically to detect this fact, it's just a simple timeout. So in reality, this user session process will be again server, and it just has a timeout. And whenever it does timeout, then it would just dump its whole state in a, say, a JSON serialization to disk, basically. So we actually don't use a database to store the game state anymore, but as you maybe spotted in the architecture overview, it's just Amazon S3, so just basically a distributed file system where we can dump this to. We need to split it up further.
Okay, so if the user crashes, you preserve their state, of course.
If the client would crash, then yeah, it would just be another timeout, or maybe it isn't even a timeout when it restarts quickly enough. But yeah.
I noticed something interesting in the Erlang code that you showed, like how you record like the deltas to the user state. For example, like you have go back, like you have a list
user
like
effects,
decrease experience, decrease energy, and does this information propagate back to the client, or is it like?
Yeah.
Is it like dual simulations running in parallel?
Yes,
okay.
It is. So that's one of the challenges in this architecture, that the client code needs to be in sync logically with the server code.
Yeah.
But you need to do that because the client will not wait for an answer from the server. It will just assume it is okay.
Yeah.
And continue playing, so the user doesn't need to stop interacting and stuff. So just needs to apply the same effects of hindsight as well.
But have you like managed to leverage this in some way? Because I find it a little bit interesting that now you have kind of separated, the state change and the state are two separate things now. So, I mean, those are kind of events which could be used to trigger other stuff. Are you using or doing something like that at the moment, or?
I mean, the events that occur are also used for, say, logging and other analysis features, of course. So this kind of the event stream is also logged somewhere else. But yeah, what did you have in mind?
No, I was thinking, because I've been thinking about this exact same approach when doing non-distributed functional programming games, like just one client, a desktop. Because, I mean, given infinite bandwidth and zero latency, I mean, you could just put all the game logic on the server, and then the client could get these messages and like, oh, I increased my experience, like make the experience bar go up, or like increase the energy, and then you could have it like be a true model view controller setup where the client is actually just a very thin client with the view and all the interesting stuff happens on the server.
Yeah.
But
in a perfect world where the internet bandwidth is kind of infinite and everyone, even playing casually, has this nice infrastructure at home.
And there's world peace and
then we could save a lot of work. True.
But on that point, I think you have enough internet bandwidth at the moment to send all these messages back and forth.
Yeah,
if people are not watching YouTube at the same time, then you're fine. You're already done.
Yeah, that's true in a way, but still, if you have a game where you have a nice interface and just continue click, then it is still a noticeable delay when you just wait for the response of the server.
Right, so delay is your problem, but bandwidth is not the issue.
Yeah, okay.
Go ahead.
Go ahead. Yeah, maybe last question.
You try to use WebSockets for your application because it will be possible to reduce feedback on the payload and get some back and forth on the client.
Yeah, we actually have experimented with WebSockets, but they are kind of awful. They just work in a very narrow kind of environment, and you need all sorts of fallbacks for when you're kind of out of this narrow thing. So they introduce more problems than they solve for us. But we are actually using server-sent events. So that's basically just chunk transfer for the communication back. But we still have requests, separate requests for the way to the API.
We're running out of time, so if you have no more questions, please ask Martin after the talk. Thank you, Martin. You're welcome.